Okay, in this video, I want to start with something called game theory. It's not exclusive to spatial analysis, but again, if you give it a spatial context, um, we can still produce aggregation and segregation from it. Okay, let's talk about game theory itself. It was invented by Van Neumann and Morgenstern in 1944. It's about conflict among thoughtful and potentially deceitful people. And it is trying to answer this question: what people should do in a situation that involves conflicting interest and joint decision making. Okay. So here, game theory, the word game, a game is a joint decision situation where people interact directly. No agents brokering the interaction. Okay, and each person's decision influences everyone else's payoff or punishment from the situation. It's a game is a zero-sum situation, which means the resource has been decided. If someone wins, the rest lose. Okay. And if a game is non-zero-sum games, it means that there could be win-win or win-lose. Okay, so a game can be zero-sum, can be non-zero-sum. Okay, and there is possibility for mind games, bluffing, deception, and trying to guess what the others are thinking. This is happening widely in gambling games, Texas Hold'em, or dice games, right? There is always bluffing, deception. You're trying to use a specific strategy to optimize your income, while other people, they need to lose for you, for your benefit, right? And there are many applications of game theory: politics, economics, business, biology, anthropology, engineering, and GIS. Okay, here is an example. It's a generic template for a non-zero sum game. So there are two players, player A and B, can be extended to n players. You will say that even for only two players, this game is complex enough. So if you extend it to n players, it's not possible for our human brain to exhaust all the possibilities. Okay, let's focus on this two-player game first. Before we start, let's just set some rules for rewards. There are 4 levels of reward: T, R, P, S. T is the largest reward, then R, then P, then S. Obviously, if you were one of these two players, you want to get T. The least option you want, the least result you want is S. Okay, so we have player A, player B. Each one can cooperate or defect. Let's just say if they both cooperate, R will be rewarded for both of them. R is the second level reward, right? If a player defects, for example, player B defects and player A cooperates, then A gets S, which is the least reward, and B gets T, which is the largest reward, temptation. It's the same thing for A. If A defects and B cooperates, B will get S, which is the least reward. A will get T, which is the largest reward. Okay, and if both of them defect, they will get P. P is the third level reward. It's okay. It's not the least one, but it's just small enough. A and B, they both will get P. So if you're one of the players, what would you do? I mean, for the whole system, for both of them, the best option is cooperate and cooperate. You both will get R. It's not the largest reward, but both players, they are safe. The reward is good enough. But this situation is pretty hard to appear because each player has desire. Okay, they all want the best reward. So it's very possible that player B will defect to get T. But there is also risk, because if you choose to defect, how about the other player? What do you think of other player? The other player will probably think of the same thing as you think, which means player A is also going to what? Defect. If you both defect, you will get P. P is much smaller than R. So that's a risk. But are you going to cooperate? Are you hoping that A is also going to cooperate? That's the best scenario. But the possible scenario is that you cooperate, the other one defects, and you get the least reward. And he or she will get the best reward. Are you going to enjoy that? No, absolutely not. So you can see here, you can choose to cooperate or defect, but the decision is pretty hard to make. And of course, you can say, okay, let's just sit down, and I will make sure that I'm going to cooperate. Can you also cooperate? And player A says, okay, yes, I will cooperate. But another question: are you going to believe A, or is A going to believe you? You're saying that you are going to cooperate, but is that a lie? Because in fact, you are going to defect. Okay, so this is game theory. This is game theory. A very classic example is prisoner's dilemma. So it's also Henry and Dave, they're A and B, but instead of rewards, here we're talking about punishment. Okay, we're talking about punishment. They are both criminals. If they both deny their crime, okay, they will get 3 months. So totally 6 months. It's okay. But if Henry says that Dave is guilty, I'm not, or similar situation for Dave, then the one accusing another one will be free, another one will get 20 years. Okay, it's best for yourself, but it's worst for the system because totally you get 20 years. If you're you both accuse you both accuse the other person, then totally you get 5 multiplied to 10 years. It's not the best for the system, but it's okay. Okay, the best scenario for the system is 3 months for each one, so totally 6 months. But this is very not likely to happen because Henry, no matter Henry, Dave, John, or Sam, no matter who, they're trying to get away from it. They will just accuse the other person. So 5 years for each person is the most likely scenario. Okay. Okay. So what's the optimal strategy here? The optimal strategy is for both to defect, even though it would be better to cooperate, because cooperation is not likely to happen. This is not likely to happen. Okay. Okay. So I mean, this is the best scenario, but in the real world, given people's desire, okay, you should defect. You should defect. And about this interesting problem, a lot of scientists, they are trying to use a specific term to address it in computer science. It's called iterated prisoner's dilemma. Okay, and which means that different scientists, they have different strategies for this dilemma, for this prisoner's dilemma, and when they are using their algorithms to compete each other, right? Each scientist has an algorithm for his prisoner, and you can say that a lot of prisoners, they are here in this pool to fight one-on-one to get the best, highest benefit from this computation, and they repeat this process because they're repeating this process. Okay, the knowledge of past plays, which means the reputation matters, because there are prisoners A, B, C, D, E, F, maybe to Z. There are prisoners 1, 2, 3, 4, 5. Maybe 1,000 prisoners from 1,000 scientists. They are competing here. And when you repeat this process, you could just encounter the same prisoner multiple times. And you should consider this prisoner's past behavior to find out an optimal strategy for this prisoner, okay? There used to be this tournament, scientists submit strategies or code for IPD, and code played against each other in simulated game. Okay, so what's the purpose of this funny tournament? To find out, of course, to find out an optimal strategy for people. Okay, it has real world meaning. And results, altruistic strategies tended to perform better than greedy strategies. Okay, you should start by cooperating, although cooperating will bring punishment to you, but then do what other player did in last round. Okay, this is the result from this tournament. Okay, but in real world, I mean, you can use this specific say conclusion to guide your behaviors in real world, but it's different from real world because this is an iterated process. You have infinite opportunities to fight again and again and again. But in real world, if you are Dave, right, you're caught, and your partner Henry is also caught, do you have another opportunity to optimize your strategy? It's yes or no, because it's at least you will have 3 months in prison, or you could have 20 years in prison. You do not have this opportunity of iteration to repeat this computation, to repeat this game again and again, to find out how Henry behaves, how Henry counters your strategy. Is not possible. So again, this tournament has real world meaning. Okay, there is a general guideline for your strategy in real world, but again, it's not real world. Okay, the general lesson here is be nice, but not too nice, forgiving and transparent. They are all not possible in real world. In real world, when people are competing for less punishment or for a higher rewards, can you be nice? Sure, it can be nice, but what is not too nice? What's the boundary here? Forgiving and transparent. Okay, when you are being transparent to other people, do you think they will consider your transparency as real transparency instead of your lies? So yeah, there is always this wall between people. People cannot fully trust each other. Okay, that's the ironic part. Okay, how to give game theory a spatial context. Okay, again, we use lattice structure, right, in that logo. And only play against your neighbors, not other cells very far away from you. Evolutionary, adopt the winning strategy in your neighborhood, right? This is actually the implementation of this part of the sentence. Do what other player did in the last round. Adopt the winning strategy in your neighborhood, which means follow your neighborhood, okay? Space and cooperation strategies tend to aggregate. So aggregation benefits cooperative strategies, which means you will say that in this model, cooperators, they are going to get together, Okay, they have experienced the benefit of cooperating. They will be stable. They will continue to cooperate, and that's aggregation. And virtuous circles of cooperation that outperform defectors caught in vicious circles of defection. Okay, here is the model. Here is the model. I will show you the rules here and different configurations here, and I will show you the model in that logo. Okay, so here we have a parameter called B, relative advantage of defecting over cooperation, which means this is a benefit you get by defecting people. Okay, when you are vicious. Payoffs of a cell based on the interaction between itself and one of its neighborhood. If a cell is cooperating and the neighbor that cell is playing now is also cooperating, they both get 1 for payoff. If the cell itself is cooperating, but the neighbor is defecting, then it gets 0. It gets 0. If the cell is defecting, but the neighbor is naive, is cooperating, the cell will get B for reward, for being vicious, for successfully deceiving the neighbor. Okay, if they're both defectors, they get nothing. Okay, how about those colors of cells? Colors, they are based on a cell's previous state and its current state. So if it is blue, it means the previous state of this cell, the previous state of the cell was cooperating, and the current state of the cell is also cooperating, which means it's a very friendly gamer. Okay, and if it is yellow, it means that the last round it was cooperating, but this round is defecting. So used to be a good people, now bad people. And the green is the opposite of yellow. Used to be a bad people, and now it's a good people. Red means that this person is very vicious, used to be a defector and still a defector. Okay, let's say this model 315. Where is my net logo? 315. Okay. Let's just go. So yeah, here is the situation. You can say that, let's just stop. You can say that most people, they are good people, say, which means that the optimal strategy actually works here, which means that if you continue to cooperate, it's best for the system. It's best for the system because if both if the cell itself and also the neighbor is also cooperating, they both get 1 rewards. Totally for this pair, they get 2 for the reward. That's the best scenario for the system, right? Right? So you can say, yeah, that's the case here. But we can see a lot of green cells, red cells, and yellow cells, they are shaking, they're blinking, which means a lot of cells, they are what? They're changing between, they're changing among what? Yellow, green, and red. But red is relatively stable, right? If we let it run for longer time, you can see that red is relatively stable. It's more frequently that those cells, they are changing between yellow and green, which means that no matter bad people, defectors, and cooperators, they do not change very frequently. Instead of that, yellow and green, these blinkers, they're changing continuously between cooperator and defector. Okay, so here, where is the aggregation? Where is the aggregation? Obviously, those red lines, those vicious people, they are forming aggregations, linear aggregations. And you can consider this blue ocean here, it's an ocean of cooperators, is also an aggregation. But you can also say that the blue cells, they are separating yellow cells, green cells, and red cells. Okay, so aggregation and segregation, again, they both exist here in this spatial pattern, in this space, okay? So spatial revolution game theory, okay? And we have discussed so many models in this chapter, okay? And these models, they all can produce aggregation and segregation. And one of the most important applications of aggregation and segregation simulation is what? Is for urban growth or urban expanding. Okay, CA and urban processes. Okay, CA models can link micro-scale processes. For example, the movement of each family, the movement of even each individual human being, to emergent global effects. Okay, we start with the movement of individuals, but eventually we care about this, the pattern, the spatial pattern of the city, of a specific city or of cities. How do they grow? How do they expand in space? Okay, and we can give different states different ideas. Okay, states, they can be used to address types of land uses: residential, commercial, industrial, etc., and etc. This is for the scenario that you use each cell for a specific area in the real world. Of course, you can use states to represent different types of people or individuals. Okay, at individual level, and we have different types of transition rules. For example, if we are talking about different types of land uses and the change of land uses, transition rules represent how land uses interact to promote or hinder change to new land uses. So states, for different states, for different types of land uses, transition rules, they are set, they are created to address the interaction between different types of land uses. That's one way to simulate urban urban spatial pattern, right? Of course, you can also use different states to represent different types of people. For example, young people, mid-aged people, elder people. Transition rules can be used to address their movement, right? Children below, say, 14 years old. Then young people between 18 to 35, how do they move? And how about elder people? For example, people about 65 years old, how do they move? You can set different rules for them and simulate how they move within urban areas, right? That's another way to address urban, right? It could be for simulation of urban life and urban or people's movement in urban areas. You can compare this pattern to people's movement in rural areas, right? So the basic idea here is that you use states to represent different to different individuals and use transition rules set different transition rules to address their movement, to address the change of them. Okay, and there are also challenges or issues you should be careful with if you use cellular urban models to simulate spatial patterns in urban areas. So a few models follow strict CA or IPS formalisms, which means that there is barely pure application of a single building block like CA or IPS. Sometimes, not sometimes. In most scenarios, you have to combine different building blocks, okay, to achieve your goals. And most models use synchronous updating. Effects of sequential updating are not very well explored by current literature. In real world, I mean, for example, when you're looking at the metropolitan, Columbus metropolitan area, if you consider that this area is put on a lattice and it is separated into cells, do you think that at a specific time all those cells will change simultaneously? Not likely, right? Not likely. So asynchronous updating is more suitable for the studying of urban areas, but asynchronous updating is more complex. Okay, so most applications of CA in urban areas, they are using synchronous updating, which is an issue because that is not what is happening in real world. Okay, and handling transportation is difficult. Transportation networks they're very special. If you want to address them on a lattice and simultaneously addressing urban change is pretty hard because the transportation networks, they cause non-uniform effects across space, which means that usually when we're creating a set of rules, transition rules for say for lattice, these rules apply to each cell within the space, but transportation is different. Okay, the effects created by transportation, by the movement of cars and individuals, they're creating different patterns, and they're using different rules across space, which means adding transportation into your urban model, CA urban model is pretty difficult. Okay, because usually when we're talking about CA models, you have a single set of rules applied to all cells across the space. They don't change. And fine-grained or high-resolution models can be pretty hard for CA, because when we are looking at a specific place with high resolution, you will see that each building has its own shape. Each park and each car has its own shape, and they should not be simply addressed by a small cell, which is a square, which means that the structure of this lattice should change. But it's not possible, because the reason why we use lattice to represent the real space is because it's simplicity. Each cell is a square. There is no difference amongst cells. And that's the simplicity. But if you are using high resolution models, which means that you can just differentiate each, say, each object, say that on the ground, then a square is not good enough to represent all objects, right? So that's a problem. And also, it's pretty hard to do model evaluation. It's pretty difficult to compare snapshot-based evaluation with real-world maps, because when we are using NetLogo, when we're using agent-based model, actually each tick We use tick to address the change of time. And after each tick, we have a specific pattern in front of our eyes. And that is a snapshot. And eventually, when the model, when you finish running the model, there is a static snapshot in front of you, showing, providing you a specific pattern. That is also a snapshot. Um, Again, it's pretty hard to compare these snapshots with real world maps, Okay. Okay, that's all I want to talk about um, aggregation and segregation. Okay, this whole chapter, chapter 3, is about using different models to produce aggregation and segregation. And in next chapter, we're going to discuss models to simulate random walks. Random walk, random walks sounds simple. Again, right? There is a people who will just um, walk on a specific direction for a specific distance or for a random distance. I mean, if it is random, what's the meaning of that? Because in real world, individuals, no matter human beings or animals, they don't walk randomly. We'll say that, okay? We'll say that in next chapter. And thank you.